We're very happy to have Diandian Peng giving updates on his recent research. Diandian is an IGPP Green postdoc scholar working with Stegman. He got his bachelor and master's degree in the University of Science and Technology of China. He earned his PhD in the University of Illinois at Urbana-Champaign in 2022 under the advisory of Li Junliu. Diandian's work is focused on the simulation of mantle flow and slab evolution using models with data assimilation. Today, he will talk about the results from global and regional mantle convection models for the circum-Pacific subduction zones. Diandian, let's get started and welcome.
Okay, thanks for the introduction, Zhe. And thanks everyone for being here. So this talk will mainly be comparing the global and regional models for the circum-Pacific subduction zones. I will talk about their results and how they are different, and which model behaves better for which subduction zone, and what's the reason for the good or better behavior. Here is a short outline. Mantle convection models is a very important way to understand the Earth by modeling the evolution of Earth's internal structures like the subduction slabs. We can know their evolution and how the surface responds to the mantle convection. In the past decades, different types of mantle convection models are developed, and they helped to solve a lot of problems. In this talk, I will compare different types of models, and the most importantly, I will focus on the circum-Pacific subduction zones, East Asia, Tonga, North America, and South America, and show the differences between the global and the regional models. And last, there will be a short summary. So models can be classified into different types by their domain, their dimension, and the ways we use to constrain the surface and under boundary conditions. For example, the simplest ones are the 2D models. The advantage and the disadvantage of 2D models is their simplicity. So they have been used to study the plume snap interaction, the double snap subduction, and as an example here, the viscosity contrast between the lower mantle and upper mantle. Expand the 2D models to 3D allows us to learn the 3D mantle flow. For example, this study shows the toroid flow near the slab edge, and also the trench width on the trench retreat rate. Global scale models, of course, is beneficial for studying global scale convections, like the upwelling of plumes and the downwelling of slabs on a global scale. Recently, with the development of plate reconstruction, there are more and more geological and geophysical data to constrain the historic position of different plates and also the seafloor age. Now the plate reconstruction models are getting better, so we can use the plate reconstruction to constrain the surface plate motion and this spherical structure. Using this as input data in the model, we can develop so-called data assimilation models. For example, this one is a regional model for the Farallon slab, and the modeled slab structures fit tomography very well. And this one is an example of a global model. So since different types of models, they have their cost varies a lot. Global models are the most expensive ones, of course. So in this talk, I will compare one global model and 4 different regional models. This figure shows plate motion and the signal edge at the background color. There are 4 boxes which shows the region, the domain for the 4 regional models. The questions that we are trying to answer is how correct are these models? And regional models, because they have sidewalls, how much they will be affected by the sidewalls. And also for different subduction zones, which type of models should we use? First, this is an overview of a global model from the Western Pacific view. In this video, the color shows the depth and these volumes shows slabs. So, I cannot play the movie again, right? Oh, okay. So this is the view from focused on the Eastern Pacific. On the Eastern Pacific, the subductive slabs are mainly the Fanon slab and Nazca slab beneath the South America. Next, I will show the comparison of the global model and for regional models. First, for East Asia, the chosen cross-section is shown on the map. On the left side, these are the seismic anomalies. These cold anomalies, they are often interpreted as the slabs. These two are the model results, the global model and the regional model. This one shows a quantitative score to evaluate how the model fits tomography. So for beneath East Asia, the most important and the most famous features for the slabs is that they are stagnant above the 660 discontinuity. And the global model produced this feature pretty well. But in the regional model, the slab penetrates into the lower mantle directly. Also, the lower mantle slab has different positions. Based on the panel E, we can see that for most depth, the global model is better than the regional model, except mid-mantle around 1,000 kilometers, because for these depths, there are not much slabs. So this evaluation have large errors. Then next, we need to discuss why the regional models cannot produce the most important feature for the East Asian slabs. Previously, we have shown that the regional mantle wind is a very important controlling factor for the formation of the stagnant slabs. For a dipping slab, it has been shown that beneath the slab and in the mantle wedge, the dynamic pressure are different. Beneath the slab, the pressure is often larger than the mantle wedge, so there will be landward push by the dynamic pressure. This is the reason why most slabs has a certain dip angle. And because of this dynamic pressure, we can see that from 140 MA to 70 MA, the dip angle of the subducted slab is getting smaller. Between 70 and 40 MA, there's an important event, which is the subduction of Izanagi Pacific mid-ocean ridge. Due to the ridge subduction, the Izanagi slab is detached from the surface. But the downward Izanagi slab left a low pressure zone above it. And then this low pressure zone induced a very strong westward Poisson type mantle flow. we name this type of flow the regional mantle wind. This mantle wind drags the subducting Pacific slab westward. So eventually, a stagnant slab is formed. From the map view, we can see that this flow is prominent from the trench all the way to mid-China. Then what's the situation for the regional model? In this figure, the left side shows the evolution of dynamic pressure and velocity in the global model, and the right one is for the regional model. So we can see that in the regional model, there isn't much pressure difference across the slab. So the deep angle of the slab is much more steeper than in the global model. In the lower mantle, this lucky slab is sinking almost vertically. But in the global model, there's a strong westward component. This major difference is mainly because of the sidewalls in the regional models. They have free boundary conditions, so the mantle convection circle are mainly local, like this. But in the global, there can be large-scale flow from the eastern side of the model all the way to the western side. So we propose that this is the major reason why the regional model cannot produce stagnant slabs. Then next we turn to another cross-section. This is a cross-section targeted on the Tonga slabs. Tonga slabs, similar to East Asia is also featured by the slab stagnation, as shown by tomography. It's interesting that both the global model and the regional model has the stagnant slabs produced. And the regional models is actually better than the global models. So, so let's look at the subduction rate and the trench retreat rate to find out the difference between Tonga and East Asia. This figure, the open arrows shows the plate motion. These arrows shows the trench retreat. Tonga is a very special region, which is featured by the farthest trench retreat. On the northern edge, it's over 15 centimeters per year. This is really fast. But for East Asia, the trench motion varies. Sometimes it's trench advance, and in some places it's trench retreat. So this is a very important difference on the plate motion history between Tonga and East Asia. From the evolution of dynamic pressure and the mantle flow, we can see that they are pretty similar between these two models. The pressure difference across the slab is not that strong, not like East Asia. So we propose that for the Tonga subduction zone, the fast trench retreat is the major reason for the slab stagnation. And in the regional model, the plate motion and the trench retreat is also imposed surface boundary condition. So the regional model doesn't vary much from the global model. In this case, the sidewalls are not a problem for modeling Tonga subduction zone in regional models. The next subduction zone is North America. This is the cross section. These are the far-long slabs in tomography models. The global model and the regional model, at the first glance, they look very similar. But if we look closely, we can see that in the regional model, the far-long slab is eastward shifted by like about 10 degrees. The fitting score to tomography also shows that these models are quite similar with minor differences. In the upper mantle, the regional model may be better. In the lower mantle, global model is slightly better. It's more clear from this map view. In this figure, the background color shows the P-wave velocity anomalies. These fast anomalies, they are the slabs. So we can see that the global model predicted the position of the slabs pretty well at both depths. But the regional model has eastward shifted slabs. One other important difference between the global and the regional models are that the horizontal mantle flow varies a lot. So in the global model, at both depths, the mantle flow velocity is southwestward, and the magnitude is about 3 to 4 centimeters per year. For the lower mantle, this is a very large velocity. But in the regional model, the velocity is very small. The largest may only be like 1 centimeters per year. So this is the reason why in the global model, the slab in the lower mantle is positioned southwestward comparing to the regional one. And this kind of large-scale mantle flow, they cannot be produced in the regional models because the boundaries, they are impenetrable. In terms of dynamic pressure, we can see that these two models are similar. They all have no pressure zone in the mantle wedge and a pressure difference across the slab. So this pressure difference, they are the major reason for the formation of flat slab beneath North America during the early Cenozoic. And considering the subduction history for North America and East Asia, there's a very important difference. These triangles on the figure shows the trench position. We can see the trench is migrating westward at a very large speed. But for East Asia, the trench only migrates like a few hundred kilometers. So for North America, the trench retreat is also playing a very important role in the mantle flow. Like for example, beneath the overriding plate, there's a mantle flow towards the trench, and this flow is consistent in the global and regional models. This is due to the imposed plate motion and the trench retreat. Also, this feature is imposed in both global and regional models. So the results are similar, and we suggest that the original model can be safely used for the subduction beneath North America. The last subduction we focused on is the large-scale subduction beneath South America. So along the South America has a very, on the western coast, it has a very long trench, over 6,000 kilometers. And along the trench, the slab structure varies a lot. There are different pieces of flat slabs, and some parts also has the stagnant slabs. This figure shows the position of the cross section here. So these two tomography suggest that there's a stagnant slab here, but different tomographies give very different results. so it's still in debate. But looking at the results in the global and regional models, the global model has produced a snap structure which is very similar to tomography. But in the regional model, the snap goes into the lower mantle directly. This is a very prominent difference. And another difference is in the global model, there are code anomalies beneath the Nazca snap. Let's recall that when we look at the horizontal flow in the lower mantle beneath North America, there's large southward components. Actually, these code anomalies, they are the fernal snaps originally subducted beneath North America, and they migrated thousands of kilometers to South America and interacts with the subducting Nazca snap. So, the match between the two models with tomography can be shown in this map view. These are the snaps in the global model. They are pretty consistent with tomography. And in the regional model, the snap is eastward shifted. On both these steps, we can also notice a strong southwestward flow in the global model, which is not presented in the regional one. This is consistent with the situation beneath North America. So connecting these two places, we can see that this is a global scale mantle flow all the way from North America to South America, and forms a circulation in the lower mantle. This kind of flow cannot be produced in the regional models. One reason is that regional models have free slip walls. The other one is the model domain is limited, so they cannot cover such a large area. In terms of dynamic pressure, these two models are similar. In both of them, in the mantle wedge, the pressure is low, and there's a trenchward flow beneath the overriding plate. So the cross-section further confirms that the up mantle flow is not the major reason for the difference of snap geometry between these two models. And the fernal snap may be the major decision factor for the formation of the stagnant Nazca snap. So last, this is a figure to summarize the effect of the boundary condition. Panel A and B shows two different scenarios. For subduction zones, the subducting speed is always pretty large. And in models with data assimilation, these velocities are imposed into the models. For subduction zones like North America and Tonga, the overriding plate is also moving pretty fast. So because of the fast plate motion beneath both the overriding plate and the subducting plate, the velocity is decreasing with depth. This is a typical coed type flow. And because these two plates are moving towards each other, in both global and regional models, the mantle flow pattern is like a circulation. So near the snap, these two types of models should have similar mantle flow, and eventually the snap sinking direction will be similar. This is the reason why for North America and Tonga, the regional models predict similar snap structures as in the global model. In another scenario, the subduction rate is still fast and induce a cold type flow beneath it. But the overriding plate is not moving much. So the flow above the snap is mainly controlled by the subduction snap. The no pressure zone will induce a personal type flow, which has the maximum velocity in the middle. And in global models, there will be a large scale flow all the way from the subducting plate to the overriding plate. However, in the regional models, because of the free slip walls, they have the flow pattern has to form a convection circle, and it's pretty localized beneath both the overriding plate and the subducting plate. As a result, the snap sinking direction in a global model tends to be more flattened, which means the snap dip angle in a global model will be smaller than in a regional model. This is why the regional model for East Asia is different from the model, the global model. And they are unaffected, like the interaction between the subducting snap with other snaps or LSVPs. These two factors are pretty large scale, and they require a very large model domain to be considered. So in the regional model, since the interaction between snaps and the LSVPs cannot be modeled as naturally generated in the global model. So the regional model for South America, because it doesn't contain Fresnel snap, the result is very different from that in the global model, and it doesn't match tomography. So based on these model results, we suggest that global models are generally better than regional models because they can generate large scale mantle flow. They can carry out the LSVPs, and they have the interactions between snaps and snap plume, and also snap plume interaction. For regions with very complex subduction history, like East Asia, it's best to use global models because regional models, they cannot take care of the subduction outside of the box, and they cannot generate the global scale flow as in global models. For other regions like Tonga and South and North America, where the overriding plate moves very fast, the imposed plate motion may play the most important role in the mantle flow, especially in the up mantle. In this case, regional models may be safe to use, and because they cost a less computational source, so we also suggest that we can use regional models for subduction zones similar to Tonga and North America. Okay, that's all. Thanks, and please feel free to ask any questions.
Thank you, Diandian. So we would first invite questions from the students.
Hey, Diandian, I have a question. Okay.
Go ahead, Shang-Chi.
Okay. So, Diandian, so it's your conclusion is that the global model is better. So why don't we just use global models because of the computation is expensive?
Yeah. A global model like this costs a lot of resources. It's like 12 times more expensive than a regional model.
So are there other strengths from regional models?
Under what?
So does regional models has some like strengths than the global model?
Yeah, regional models. Running a regional model is much cheaper than a global model. This itself is a very, very good advantage.
Except this one reason, any other?
In a regional model, it would be very easy to test different parameters. Like one parameter is the viscosity, which has very large uncertainties, and we know very little about it. By running regional models, we can test a lot of viscosity structures.
Okay, thank you.
Thank you.
So Gina.
Hi, thanks for the interesting talk. I just am not very familiar with this type of dynamic modeling. So I'm just curious whether the only difference between the global and regional simulation, the difference is just about the boundary condition that drive the difference on the correctness, or are there other additional data sets that are available in global simulations not used in regionals or something like that?
In this talk, they are only except for the limited model domain for the regional model. Another difference is the global model has a thermochemical layer above the common boundary to simulate the formation of LSVPs. But the LSVPs, they are like hemispheric structures. So in the regional models, I don't include such a layer. Except for this, there's no difference between the global and regional model.
Then could those thermochemical layers can also play a critical role together with the side walls?
Yeah, that's possible. I use the South American slabs as an example. This is the global model. This reddish area, they are the hot anomalies. This is the LSVP. It's not in the regional model. So there is a possibility that the LSVP also affect the subducting slab. But the reason that I don't include such a chemical layer in the regional model is for regions like North America and East Asia, tomography models don't show LSVPs. So it's not good to include such a layer in the regional model because it will artificially make the model look bad.
Okay, thank you.
Jeremy. I think Jeremy asked the question in the chat. Are there any model simulation on different domain, like taking global model as boundary and initial condition and run a regional model?
This is a very good question. I have shared this global model with a collaborator, and he has tried to take the temperature structure from the global model as an initial condition for the regional model. And this test is done for East Asia. This method improves the results for the regional model, and it's a very huge improvement. But I think another important factor to consider is the velocity. That test doesn't consider the velocity if we also take out the velocity from the global model as boundary conditions in the regional model. I think the results should be better.
Tianze.
Sorry, sorry, I'm muting myself. Can you show the conclusion slide again?
Yeah.
Oops.
Wait a second. Yeah.
Okay, so I'm a little bit confused over the top slide where you have imposed surface velocity at the free surface. Is that realistic, or it's just a model assumption? Because in reality, plate tectonic is certainly not driven by some force applied on the free surface, right?
Yeah. This is just a sketch. So the imposed surface velocity means in the model setup. In reality, the plate motion should be driven by the subduction slab. But at the counter stage, the data assimilation models always have imposed plate motion from plate reconstruction models.
Ah, I see. So this is just how your model works.
Yeah,
not the reality.
Yeah, it's kind of a model input.
I see. Thanks. Actually, I have another. Actually, I have another question. Back to your slide showing the subduction beneath South America. It looks like the seismic tomography models don't show the Farnham slabs swept southward, right? Or
the argument, I actually didn't find many studies about the Farnham slab beneath Nazca slab, but in both these two tomography, there are some fast anomalies here.
Okay.
And the position is pretty consistent with the global model.
I see.
And this may be the Farnham slab.
Okay. Thanks.
Any more questions? Okay, if there's no more questions, let's thank Diandian for the great talk.
Thank you.
Oh, I found Andrea has a question. Oh, okay, sorry.